All right, let's do some examples that have us tell the electron domain geometry, and not only do that, but draw the Lewis structures itself. Let's start out with AsF5. So we have arsenic right here, and then we have pentafluoride right here. So step one tells us to count up our valence electrons. For arsenic, we have 5 valence electrons plus we have 7 valence electrons for each fluorine times 5. 7 times 5 is 35 and 5 more. We've got 40 electrons we get to play with in our structure. All right. Step 2, we're going to put the different one in the middle. So we're going to take arsenic and we're going to join 1, 2, 3, 4 fluorines, and we're going to have to join a 5th fluorine. It says we've got to attach 5 of those. We just used up 2, 4, 6, 8, 10 valence electrons. I'm going to take away 10. I've got 30 left. Let's put those on the outside. So we say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I've run out of electrons. I have no electrons left. Step 5, check. Does my center have an octet? Arsenic actually has more than an octet. It has 2, 4, 6, 8, 10 valence electrons. Is that okay? The answer is yes. It is okay because arsenic is in the 3rd row or below. It can expand its octet and have more than 8 because it has those d orbitals that we can use for bonding as well as the s and the p orbitals. So there's my Lewis picture. If I want to know the electron domain geometry, I'll call it, E minus domain geo for short. I look at how many domains I have on my center atom. It looks like I've got 1, 2, 3, 4, 5. The electron domain geometry for 5 things is 1 up, 1 down, 3 in a ring around the middle. This is a pyramid on the top, a pyramid on the bottom, bipyramidal with a triangle base. So we call it trigonal bipyramidal or pyramidal. So there is your first example. Angles, up to the ring around the middle is 90 degrees, and then a ring split 3 ways around the middle is 120. There's your first example. Let's try another one. What if I gave you selenium tetrafluoride, SeF4? Selenium is in group 6A, fluorine is in group 7A. Step 1, let's add up our valence electrons. Selenium, being in group 6, has 6 valence electrons, plus we have 4 fluorines, each with 7. 7 times 4 is 28, plus 6 more gives us 34 to play with. Step 2, put the different one in the middle. We're going to stick selenium in the middle. Se goes in the middle, and we connect the fluorines with single bonds. 3, 4. We just used up 2, 4, 6, 8. We're going to take away 8 from our tally, and we're going to have 26 left. Step 3. Fill the octets of the outer atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're going to take away 24 electrons. We've got 2 left over. Step 4, leftovers go on the middle as a pair. So we're going to put them anywhere on the middle as a pair. That makes selenium have more than 8 electrons, but since it's in the 3rd row or below, that is okay. So there's our Lewis structure. Now, as for the electron domain geometry, we need to count our domains. We have 1, 2, the lone pair is a domain, that's 3, 4, 5 domains. 5 domains is 1 up, 1 down, 3 in a ring around the middle. That is a pyramid on top, a pyramid on the bottom, bipyramidal, with a triangle base. So we call this geometry trigonal bipyramidal. Okay, there's example 2. Let's try another one. What if I gave you HCN, hydrogen cyanide? Step 1, we got to draw the Lewis picture. So let's add up our valence electrons. Hydrogen has 1 valence electron. Carbon has 4 valence electrons. And nitrogen right next to it has 5 valence electrons. So we have 10 valence electrons to play with, 5 and 5 more. Put the different one in the middle. I'm going to go ahead and put carbon in the middle. Hydrogen can't be in the middle. Carbon is a great metal. So carbon's in the middle. We just used up 2, 4. We're going to take away 4. We've got 6 left. It tells us to fill the outside octets next, but do not put any on hydrogen. Hydrogen is a baby. Hydrogen is full with just 2. It can't handle anymore. No extra ones on hydrogen. We're going to put them on nitrogen. Fill the outsides before the insides. 2, 4, 6. I take away 6. I have none left to put on our center atom. Step 5 says, check, does your center have an octet? If you look at your center, it does not have 8. It only has 2, 4. So we're supposed to swipe from the rich, nitrogen's rich, and share with the poor. I'm going to swipe from my rich and share with my poor. Okay, carbon's still not good, 2, 4, 6. I'm going to swipe from the rich and share with the poor. Now carbon has 2, 4, 6, 8. That's good. Nitrogen has 2, 4, 6, 8. Perfect. So the neatly drawn Lewis structure looks like this. Now, if I asked you for the electron domain geometry, look at your carbon atom, your center. There are 1 domain and 2, just 2 domains. 2 domains trying to get as far away from each other as possible lets them go 180 degrees apart. These will try to arrange themselves in a line. Therefore, we call this geometry linear. All right, let's do another one. All right, what if I gave you boron trifluoride? Step 1, let's add up those valence electrons. We have a boron and fluorine. Boron has 3 valence electrons, plus we have 3 fluorines. Each fluorine has 7 valence electrons. 7 times 3 is 21, and 3 more. That gives us 24 electrons to play with. All right, put the different one in the middle. We're going to put boron in the middle and connect single bonds to our fluorine. 2, 4, 6. I'm going to take away 6. I've got 18 left. Fill the outsides. 2, 4, 6, 8, 10, 12, 14, 16, 18. Leftovers go on the middle. I don't have any leftovers. Then we're supposed to check if our center has an octet. It does not. So normally we swipe and share. However, boron is an exception. Hydrogen only makes 1 bond. Don't make it have any more. Beryllium only makes 2 bonds. Do not force beryllium to have more. And boron only makes 3 bonds. Do not make it have more. So this is a good picture, even though boron does not have an octet. We have 3 things that want to get as far away from each other as possible. 3 things trying to get apart from each other makes a Mercedes sign, flat triangle. We get a triangle here where each of those is trying to get 120 degrees apart. Now, instead of saying flat triangle where you have a boron, a fluorine, and a fluorine, The fancy word for flat triangle for the electron domain geometry is trigonal instead of triangle, planar instead of flat. Trigonal, planar, electron domain geometry. All right, let's go ahead and do another one. What if we'd had carbon dioxide, CO2? Let's go ahead and add that up. Carbon has 4 valence electrons, plus oxygen has 6 valence electrons, and we have 2 of those. 12 times 2, 6 times 2 is 12, plus 4, 16 total. Carbon goes in the middle. We connect oxygens to either side. We just used up 2, 4. I'm going to take away 4. I've got 12 left. Outsides before insides. So we go 2, 4, 6, 8, 10, 12. I take away 12. I have none left. So I can't put them on carbon. So then we ask ourselves as a last question, does our center have an octet? Carbon does not have an octet. It needs 4 more electrons. It has 2, 4. So swipe from the rich, share with the poor. Carbon's still not good. It only has 2, 4, 6. So swipe from the rich, share with the poor. Carbon now has its octet, and each oxygen still has its octet. So what is the electron domain geometry? Carbon has 1 electron domain, 2 electron domains around it. 2 electron domains are going to try to get as far away from each other as possible, and that is 180 degrees. That puts those 3 elements all in a line, and this is called a linear electron domain geometry. All right, one more. Let's try the carbonate atom, ion, carbonate ion. Step 1, add up your valence electrons. Carbon is in the 4A group. It has 4 valence electrons. Plus, we have 3 oxygens, and oxygen has 6 valence electrons. And we have a 2 negative charge. So we get to add 2 electrons wherever we want them. I'm going to go ahead and put 2 right here. So we've got 18, 2 more is 20, and 4 more is 24 electrons to play with. Step 2, put the different one in the middle. My different one is carbon. I'm going to go ahead and attach single bonds to my oxygen. I just used up 2, 4, 6. Take away 6, that leaves me with 18. Next step, outsides before insides. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've run out of electrons. Leftovers, I don't have any to put on the middle. Then your last step, check. Does your center have its octet? No. So you're supposed to swipe and share. But swipe and share from which one? I only need to swipe and share once. It looks like I have 3 equivalent options. Therefore, I have to draw 3 structures. This is a resonance example. So one of my pictures will look like this with a double bond on the left. The other ones have single bonds, a double-headed arrow. Then I'm going to draw my 2 other structures where I have the double bond in the alternate positions. My last picture is going to look like this. Oxygen and oxygen. Now, really, the true molecule is a blend of all those 3 molecules together. They are 3 bonds that are exactly the same length, stronger than a single, weaker than a double, more like a bond and a third. Now, if I asked you for the electron domain geometry, you just need to look at how many domains are attached to that carbon. It looks like we have 1, 2, 3 domains attached to the carbon. 3 things getting as far away from each other as possible is a Mercedes sign. That is a flat triangle. and we call it trigonal instead of triangle and planar instead of flat. I hope that helps. Take care.